Today, we're taking a look into a practical topic, verbal inequalities in two variables. We're all familiar with phrases like at least, no more than, or greater than. In math, these phrases translate to inequalities that describe a range of possible values. But what if we're working with two variables instead of just one? This is why in this lesson we are going to talk about how to turn real-world phrases into inequalities with two variables and then graph them to find the solution region. Here's what we'll focus on. First, we need to translate the verbal phrases into inequalities, which means when we see phrases like at least, no more than, greater than, or less than, we can translate them into mathematical inequality symbols. The next step is to decide what each variable represents in the problem. For example, if a problem says, the profit from sales must be at least $500, we might let y represent the total profit, while x could represent the number of items sold. Then, we could interpret the key phrase, at least $500, as y greater or equal to 500. Once we define the variables, we can set up an inequality with two variables. For instance, let's say we know each item generates $20 in profit, plus an initial setup cost of $50. If the profit must be at least $500, we could write this as y greater or equal to 20x plus 50. Now, after graphing the function, we can see that y is greater or equal to 20x plus 50 is presented with a solid line. If y was strictly greater, we would use a dashed line. At the end, to show the range of values, we're gonna shade above the line. Let's see how this works with our first problem. A school fundraiser requires at least 200 items to be sold. Let x represent the number of items sold, and let y represent the total funds raised. Each item sold contributes $10 to the total funds. Write an inequality to represent this situation. First, let's define what each variable represents in this scenario. We're told that x represents the number of items sold, and y represents the total funds raised. The phrase at least tells us that the number of items must be 200 or more. Mathematically, this means we need an inequality symbol that represents at least, which is greater or equal to. So, we write x is greater or equal to 200. Now, let's focus on the total funds raised, y. Each item sold contributes $10, so we can write the expression for total funds as y equals 10x, where y depends on the number of items x. This expression allows us to relate the number of items sold to the total funds raised. Finally, we can put the information together to form our inequality. Since the total funds y depend on the number of items sold x, and we know that at least 200 items must be sold, we combine these to get y greater or equal to 10 multiplies by 200. By simplifying this, we get that total funds raised is greater or equal to 2,000. This means that the fundraiser will meet its goal only if y is at least $2,000. In our second problem, a coffee shop is creating a new blend by mixing two types of coffee beans. The premium coffee costs $15 per pound, and the regular coffee costs $10 per pound. The shop wants the blend to cost no more than $12 per pound. Write an inequality to represent all possible combinations of x and y that keep the cost of the blend at or below $12 per pound. First, let's clearly define each variable in this context. We'll let x represent the weight of the premium coffee, and y represent the weight of the regular coffee, both in pounds. Our goal is to find combinations of x and y that meet the cost requirement. The problem states that the blend's cost should be no more than $12 per pound. In mathematical terms, no more than translates to less or equal to. So, we'll need an inequality that represents this upper limit for the blend's cost. Now, let's write an expression for the total cost of the blend. Since the premium coffee costs $15 per pound, the cost of x pounds of premium coffee will be 15x. Similarly, the regular coffee costs $10 per pound, so the cost of y pounds of regular coffee is 10y. The total cost of the blend can be expressed as 15x plus 10y. To find the average cost per pound, we'll divide the total cost by the total weight of the blend, x plus y, which gives us the following expression. Since we want the average cost per pound to be no more than $12, we can set up this inequality. This inequality tells us that the average cost of the blend per pound should be $12 or less, based on the weights x and y of each type of coffee. To make this inequality easier to work with, let's eliminate the fraction by multiplying both sides by x plus y. Now we distribute 12 on the right side. Next, we'll bring like terms together by subtracting 12x from both sides. Therefore, this inequality represents all possible mixtures of the two types of coffee. For the final example, a factory produces two types of gadgets, Type A and Type B. Each Type A gadget requires 3 hours of labor and costs $5 to produce, while each Type B gadget requires 5 hours of labor and costs $7 to produce. The factory has a maximum budget of $210 for production costs and a maximum of 100 labor hours available. Which of the following inequalities represents the constraints for production? First, let's start by defining the variables in this context. We'll let X represent the number of Type A gadgets and Y represent the number of Type B gadgets. There are two main constraints, a maximum of $210 for production cost and a budget limit of 100 labor hours. Let's set up an inequality for each constraint. Each Type A gadget requires 3 hours of labor, so producing X Type A gadgets will require 3x hours. Similarly, each Type B gadget requires 5 hours, so producing Y Type B gadgets will require 5y hours. Together, the total hours required for both types is 3x plus 5y. Since the factory has a limit of 100 hours available, we can write the following inequality. Now, let's look at the cost constraint. Each Type A gadget costs $5 to produce, so the cost of producing X Type A gadgets is 5x. Each Type B gadget costs $7, so the cost of producing Y Type B gadgets is 7y. Together, the total production cost is 5x plus 7y. Given the maximum budget of $210, we write the second inequality. Now that we have both inequalities, we can express the constraints as a system of inequalities. This system represents all possible combinations of Type A and Type B gadgets that satisfy both the labor and budget constraints. Let's examine each option to find the correct answer. First, option A. This option incorrectly uses the budget limit with the labor hours inequality and vice versa, so it's incorrect. Second, option B. This option reverses the inequalities by assigning the 100 hours to the cost inequality and the $210 to the labor hours, so it's incorrect. Next, option C. This option assigns the budget limit of $210 to the inequality 5x plus 7y less or equal to 210 and the labor hours limit of 100 to 3x plus 5y less or equal to 100, so this is the correct answer. Finally, option D. This option also reverses the constraints, applying the budget constraint to labor and vice versa, so it's incorrect. The correct answer is option C. Let's quickly recap the main concepts we covered on translating verbal inequalities in two variables and setting up constraints. First, identifying key phrases and symbols. Recognize phrases like at least, or no more than, which translate to the certain inequality symbol. Knowing these phrases helps us convert real-world situations into mathematical inequalities. Second, defining variables. Clearly define each variable before setting up your inequality. Understanding what each variable represents makes it easier to create an accurate inequality from verbal descriptions like in our first example, Y represented profit and X represented items sold. Third, setting up inequality expressions. Once variables are defined, write expressions for each component, such as total cost or total hours. Combine these expressions to form an inequality that represents all constraints given in the problem. Finally, creating systems of inequalities for multiple constraints in complex scenarios, combine inequalities into a system to represent multiple conditions. This helps us visualize and solve for all possible solutions that satisfy the constraints. With these steps, you're ready to tackle verbal inequalities in two variables. Keep practicing, and see you next time.